Large language models are fundamentally constrained by the memory wall. As parameters scale into the billions, moving high-precision weights from memory to compute units burns massive amounts of energy and time. What if we could shatter this bottleneck entirely? Enter BitNet, a revolutionary architecture that proposes replacing 16-bit floating-point weights with just 1 bit. Let's explore how extreme quantization is reshaping efficient computing. In standard transformer architectures, models rely on FP16 or BF16 precision. Every dense linear layer performs complex mix multiplications involving highly precise, memory-heavy floating-point arrays. The problem: generating tokens one by one is memory bandwidth bound. Most of the GPU's time isn't spent doing math. It's spent waiting for these massive weight matrices to stream from high-bandwidth memory into the compute cores. To solve this, researchers introduced the 1-bit transformer. Instead of storing 65,000 possible values per parameter, the core idea is to constrain the weights to just 2 states, +1 and -1. By representing weights with a single bit, model size drops drastically. But more importantly, the fundamental math of the neural network transforms from complex arithmetic to simple logic. The foundation of this architecture is the bitlinear module. It is designed as a drop-in replacement for the standard PyTorch linear layer. During the forward pass, a standard linear layer computes W times X plus a bias. In bitlinear, the weight matrix W is binarized on the fly, drastically altering the computational graph, while aiming to preserve the network's representational capacity. How does this binarization work? The continuous, high-precision weights are passed through a signum function. If a weight is greater than 0, it becomes +1. If it's less than 0, it becomes -1. To maintain stability, the weights are first centered by subtracting their mean, and a global scaling factor is computed to recover the approximate magnitude of the original tensor. While weights are binarized, activations remain in slightly higher precision, typically 8-bit integers. This is achieved using absolute maximum quantization. The input tensor is scaled by its maximum absolute value, and then quantized into the int8 range. This asymmetric design 1-bit weights and 8-bit activations preserves critical variance in the input data, while still unlocking massive performance gains in the matrix multiplication. With weights reduced to +1 and -1, the magic happens in the forward pass. Traditional matrix multiplication requires power-hungry multiply-accumulate, or MAC, operations. But multiplying an 8-bit activation by positive or negative 1 doesn't require multiplication at all. The entire dense layer collapses into basic addition and subtraction. This completely eliminates floating-point multipliers from the data path. But there is a catch. The sine function is non-differentiable. Its derivative is 0 everywhere except at the origin, meaning backpropagation would normally stall. BitNet bypasses this using the straight-through estimator. During the backward pass, the gradient simply passes straight through the sine function as if it were an identity function, allowing the optimizer to successfully update the weights. Crucially, the optimizer does not operate on the 1-bit weights. Throughout training, the model maintains a set of high-precision, latent weights. During the forward pass, these latent weights are quantized to 1 bit. Gradients are then computed and applied back to the high-precision, latent weights. Once training is complete, only the 1-bit weights are needed for incredibly fast inference. An advanced variant, BitNet B158, introduces a third state to the weights, 0. By rounding weights to -1, 0 or +1, each parameter consumes roughly 1.58 bits of information. Including 0 is a game changer. It allows the network to explicitly filter out features by ignoring certain activations completely, leading to better representational power with almost no extra computational cost. The most impressive part of BitNet is its scaling laws. Historically, extremely quantized networks suffered severe accuracy degradation. However, research demonstrates that starting around 3 billion parameters, BitNet B158 begins to strictly match the perplexity and downstream task performance of full FP16L Llama architectures. The performance gap vanishes at scale. The hardware implications are staggering. Compared to a baseline FP16 model, BitNet B1158 reduces memory consumption by over 3 times and cuts energy usage of matrix operations by up to 71%. Because addition is so much cheaper than multiplication, the energy savings compound, making this architecture a monumental step forward for green AI and mobile edge deployment. To actually realize these speedups on modern GPUs, custom CUDA kernels are necessary. Standard deep learning libraries are highly optimized for FP16 and INT8 multiply accumulate operations, not ternary additions. Engineering specialized software to efficiently pack these 158-bit weights and route them through the ALU as addition operations is the final hurdle to unlocking hardware-level throughput. The era of high-precision parameter scaling is facing extreme diminishing returns. By proving that 1-bit and ternary transformers can match FP16 baselines at scale, BitNet paves the way for a new paradigm. Models of the future will be smaller, faster, and radically more energy efficient, democratizing access to massive-scale AI.